That's okay. And there's a bell in it, so.
It's hot.
All right, it'll be better once we turn the AC back on. Okay. Do you guys remember how to read this out loud?
No.
Okay. All right, so the limit as x approaches c, that means the f of x approaches L. Okay. So far, so good? All right, now this right here is the Greek letter epsilon. It is the lowercase Greek letter epsilon. You do not draw it like that, even though that's how it looks typed, because that's something else. The way that we draw it is, like Thomas said, a backwards 3. So you write it like that, okay? And then this is delta, a lowercase delta, and you could think of it as an 8 that didn't finish. I don't know how to draw that very well. Like, I draw it, but it's like not pretty. Every time I draw it, looks a little different. So it's whatever. Okay. So epsilon is a small positive number. And so the formal notation, like the math notation that we use to represent that f of x is approaching L, is we say that f of x is in between L minus epsilon and L plus epsilon. So if epsilon is a very, very small number, then you'd say f of x is somewhere in between L minus a very, very small number and L plus a very, very small number. So this is that idea of like, it's the y coordinate that really should be there. L would be like that y value, but it's not quite that y value. It's just like super close to it, okay? And then they write this as f of x minus L is less than epsilon. Yeah, but epsilon is so much easier to write than delta. When you get into like college math where they're using all sorts of Greek letters all the time, it feels like learning the alphabet again, because you have to figure out like, how do I write delta? Not like how is it printed, but how do I write that in my handwriting? You know what I'm talking about. You have to like learn. Yeah. All right, delta is a positive number. I'm positive that delta is a positive number. Right. And actually, Isaiah, I'm going to kick you out because you're not allowed to learn this. You have to do series. I'm sorry. Bye. No fun stuff for you. No fun things for Isaiah. Yes. Yeah, he was near death, and that's why he does not get to be here. All right. So, the formal notation for x approaches c means that x is either in the interval, so this is me saying like these are x values, right? Kind of like a domain. It's either in the interval c minus delta c, can you do it from online? Okay, I'll print you one as soon as I can. So this is saying it could either be like slightly to the left of c. Does that make sense? An x value that's a little bit to the left of c, because c minus delta would be a small number that's like a little bit less than c in c. Or it could be from c to c plus delta. Sorry. And so the way that we write that is we say 0 is less than the absolute value of x minus c, which is less than delta. So the point of this is to say that as x gets really close to c, it's not exactly at c. It could be a little bit to the left or a little bit to the right, but it can't be c exactly. Okay? So the reason that we don't write this inequality, why don't we write it as x minus c is less than delta? And the reason we don't write it like that is because if you wrote it like that, then your x value could be c exactly, and that's not how limits work. Okay? So x cannot equal c. So we have to have okay, do you guys agree yet that delta is harder to write?
Well, actually, yes.
Yeah. I think it's harder to write like fast.
Yeah.
The backwards threes, I'm good with those. I can write
Those
that.
are just like
Yeah.
cursive.
Yeah. It's like a cursive E. Yeah, exactly right. All right. So here is a picture of what we typically see when we read this definition. So this is like the official formal definition of a limit. We would have learned this in the very first unit of calculus on like the third day, if we had learned this where it fit in the curriculum. But we didn't learn it because, as you may have noticed, it was not on the AP exam. Did you guys notice that? You didn't see this anywhere? Yeah. So the statement, the limit as x approaches c of f of x is L, means that for each epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus the limit is less than epsilon. And wouldn't that have made a lot of sense on the third day of school? You would have been like, yeah, I totally get that. So here's the picture that they're talking about. This would be like the exact point, a c value or an x value of c and a y value of L, right? So they're saying if you can kind of squish this in this way, or actually I guess it starts here. If you can find an x value that is between like delta to the left and delta to the right, then there are corresponding y values that are right in between there. Okay? That's kind of what they're saying. So the idea of that is we might not get the exact, we can't get x exactly equaling c, and we can't get the y exactly equaling L, but if we have small enough numbers for our epsilon and for our delta, then we can make a pretty good approximation of what we think that is. Does that make sense? Okay. All right, so go ahead and turn the page. We're going to do some examples. All right, so some problems will just ask you to figure out what your delta should be. And then some problems will actually have you prove that a limit is truly the limit, okay? And so they're going to have two basically different processes. So first, we're going to do this one where you solve for delta because it's a little bit easier. So they said that the limit as x approaches 3 of 2x minus 5 equals 1. Do we agree with that? Yeah, because if you plug it in, it's reasonable, right? Equals 1. Okay, so now, then they have this. They have f of x minus the limit, right? Because f of x is 2x minus 5, the limit is 1. F of x minus the limit is less than epsilon, so that means that the epsilon for this problem is 0.01. Reasonable? Okay, so to find our delta, we're always going to start the same way. We're going to say f of x minus L is less than epsilon. And then we're going to simplify it, and our goal is to get our absolute value to x minus 3. We need it to simplify to be x minus 3. So what I'm going to do next is I'm going to say 2x minus 5 minus 1 is actually 2x minus 6. And then I could factor out a 2. And I can take this 2 and I can pull it outside of the absolute value because it doesn't make a difference. All right? Is that a frown because we're confused or just not sure why we can do that? Yeah. If it was negative, but if it was negative, you could still pull it out. You just pull out the positive version because it would affect the number the same way. So I'm going to call this 2 times the absolute value of x minus 3. And then I'm going to go ahead and divide by 2. And so I get x minus 3 is less than 0.05. Does that all make sense so far? Okay, and that's my delta. Oh, yeah. Sorry. That's it. So these are the nice problems because we didn't do a proof, so we didn't have to be like crazy formal about it. We were just solving for delta, and that's it. We're good. Now, the next example says use the epsilon delta definition of a limit to prove the limit. So now we actually have to do a proof, okay? So we're going to start off the same way, though, because to do the proof, we have to know what delta equals. So I'm going to start it off, and I'm going to say f of x minus the limit, so minus 4, is less than epsilon. And the reason I'm going to put the e in there for epsilon is because I don't actually know what epsilon is. They gave it to me in the first example. They did not give it to me this time. Okay, what do I do next? Plug in the 3x minus 2. Okay, what do I do next? Okay, so I have 3x minus 6. Factor out the 3. And if you notice this is what I want in my absolute value. I want to have x minus 2 because 2 is my c value. So my goal is to have some sort of x minus 2 is less than a delta. Does that make sense? Okay, so let's go ahead and finish it. What should I do now? I can take out the 3, and I can go ahead. I'm not going to move it to the front this time. I'm just going to divide it over since we know that it kind of works like that. So I'm going to say x minus 2 is less than epsilon over 3. And so this is my delta. Okay. Backwards 3 over regular 3. Okay, so now we have the answer. We know what delta is. Now we have to write it as a proof, and this is where things feel a little bit funky, okay? So here is how we write the proof. We are going to say, given an epsilon that is greater than 0, and we do that because, remember, the definition of epsilon is that it's a small positive number. So given epsilon is greater than 0, let delta equal epsilon over 3. No. Right. If 0 is less than absolute value of x minus 2 is less than delta, which equals epsilon over 3, then, and we're going to show our work, okay? And basically what we're about to do is we're about to write these steps backwards, okay? So we're going to say then absolute value of x minus 2 is less than epsilon over 3. And 3 times x minus 2 is less than epsilon. You see what I'm doing there? And 3x minus 6 is less than epsilon. And 3x minus 2 minus 4 is less than epsilon. So f of x minus 4 is less than epsilon, and my proof is complete.
Just like that, where you just listed that.
Mm-hmm. So this is the majority of the work, but you don't have to show any of that. This is the answer. Okay? Now, typically what I do is I break this up into 2 parts. I call this part 1, and I call this part 2. Part 1 is where I do my thinking. Part 2 is formal and feels pointless. It's kind of like, well, duh. But it's what you do. Okay, let's try another example. This one's going to be a little bit more weird. And then we're going to be done, and that's going to be it. I'm sorry it's hot. I'll turn on the AC in 1 second. I'm feeling like teacher guilt over here because I'm roasting too. All right, so let's go ahead and start this. What should we write? So we have f of x minus 4, because that's our limit, is less than epsilon. And then we plug our f of x in. We got x squared minus 4 is less than epsilon. Okay. And then I heard somebody say it. We're going to factor this. How does that factor? X plus 2, x minus 2 is less than epsilon. And which one of these are we trying to get at? The x minus 2, because our c value is 2, and we want to have x minus c. So x minus 2 is the one we're really getting at. Okay, we're going to show some work here. We're going to say that x minus 2 is less than or equal to 1. So what they do is they say, in a situation like this, where you cannot easily isolate the epsilon, you're going to take the factor, the one that you're trying to look for, and you're going to say it's less than or equal to 1. I think that's that idea of that small positive value. Okay, so that means I have the inequality that x minus 2 is in between positive 1 and negative 1. Does that make sense? Okay, and then I'm going to go ahead and add 2 to each side. And by each side, I mean all 3 sides. Sorry, let me zoom in. Didn't mean to make you squinty. Okay. So now I have 1 is less than or equal to x is less than or equal to 3. But the one that I'm trying to get rid of says x plus 2. So what I'm going to do is I'm going to add plus 2 to all of these. So I started off with the one that's my goal. That's what I started off with. But I'm manipulating it until it becomes the other one. Okay? So that means that x plus 2 is somewhere between 3 and 5. Okay? So now I can say x plus 2 is less than or equal to 5. Okay? I do that. You'll see in a second why I do that. So that I want it to equal.
Okay.
And I said it's less than or equal to 1. And I think that we do that because epsilon is a small positive value. So you wouldn't want to say 10 because there's much smaller values to work with. Okay. All right, so now what we do is we say if this was x plus 2 times x minus 2, and that is less than epsilon, and we have x plus 2 is less than or equal to 5, then I'm going to say that x plus 2 times x minus 2 would be less than or equal to if I had 5 times x minus 2. So what I'm doing is I'm saying if I have this inequality right here and x plus 2 is less than 5, then this inequality over this part over here must be smaller than this part right here. And both of those must be less than epsilon. It's a little bit weird, but you'll see why in a second. So it just adds a little step. And now if you look at this, do you see how it's kind of like the last problem? So now what do we do? So now we're going to go ahead and say, okay, x minus 2 is less than epsilon over 5. And that's our delta. Okay, so now we say, let's go ahead and write the proof. That was part 1, that was the work. And now we're going to do part 2, we're going to do the proof. And so I'm going to say, given epsilon is greater than 0, let delta equal, and anytime you do this step where you say x minus 2 is less than or equal to 1, which is basically anytime you have like an extra x in your problem. It could be from factoring, it could be from like a rational expression, maybe you have like x plus 5 on top, x minus 2 on the bottom. Anytime you have something extra like that, you're going to say let delta equal the minimum of 1 comma epsilon over 5. So they're just saying the smallest value between 1 and epsilon over 5. Okay? And it's always 1, and then it's always the answer you just got. Yeah. 1 comma epsilon over 5. So we're going to say if 0 is less than x minus 2, which is less than delta, which equals the minimum of 1 comma epsilon over 5. So this is me, I'm just being formal about my notation. Then we have x minus 2 is less than epsilon over 5. And 5 times x minus 2 is less than epsilon. And x plus 2 times x minus 2 is less than epsilon. And x squared minus 4 is less than epsilon. So f of x minus 4 is less than epsilon, and our proof is done. Okay, so I found this part down here on a math professor's website, and I liked it. So it says, rewrite the goal. Now, we didn't do that, but you could do that up here. You could say, if I have an epsilon greater than 0, I need to find the delta. So rewriting the goal would be kind of like, it's kind of like this part right here. And then it says, step 2 is to simplify f of x minus L and rewrite as m times x minus c. So what you noticed is we did that both times. That's this part right here, where you simplified your f of x all the way down and had some sort of coefficient there. And then it says bound m in terms, not today, sorry. And then it says bound m in terms of delta normally using a triangle inequality. This idea is what it's talking about with triangle inequality. That's an inequality where you have something in the middle you're solving for and two numbers on each side. So that's not anything you haven't seen, you just probably haven't heard it called that before. And then it says, if necessary, assume that delta is less than or equal to 1 so that you can get this sort of thing happening. That's exactly what we were doing before, okay, that part where we said x minus 2 is less than or equal to 1. And then it says choose, so you can see we did all of those things, right? And that's part 1, that's kind of solving for your delta, but in formal notation. And then to write the proof, you say, given e is greater than 0, let delta equal something. And then you say, if 0 is less than the absolute value of x minus c is less than delta, then something. These are all the steps we showed. So f of x minus L is less than epsilon. So this is like the proof part. And then the note I wrote down here is that part 2, this is the answer. So that's what I said before. This is the work, this is what we really care about, we think. But technically, this is the answer, and this part does not have to be shown at all. Technically. Okay. That's all I have for the examples. Let me get you an assignment you can slowly, calmly work on.